to a subtree of this node, only after every element in the subtree has got its start time and finish time, this will have the start time and finish time. So it will enclose basically. So this is called as the parenthesis theorem. This is one of the very big uses of DFS. So okay. So next is uses of discovery and finish times. Basically this kind of parenthesis can be used in many problems. Say an example.
Okay, like if you are given a tree and the operation that you can define is increment node, that is, let's assume that you store rice grains in each node. The operation that you can define is, or let's say that people live in the 3 cities, and the operation you can define is a new child is born at any city, and the query you must do is what is the number of people in the subtree rooted at some u. So obviously we need something which is better than n squared, and if you're so we need a data. This has to be solved using some data structure, but how to convert this graph problem into a data structure problem is by using discovery times and finish times. We leave this as an exercise. You can probably, that is, it is a very basic exercise once because I'm now told that it is using discovery times and finish times, and you can use some data that we will discuss in basic data.
Okay. One example I'll give is, you are given a tree. So basically the tree is given, and you are given many queries of the form. You are given 2 nodes u comma v. Tell whether u is an ancestor of v. You know what is an ancestor, right? In a tree, for u is an ancestor of v if v occurs in the subtree rooted at u. So a tree is given and many queries of the form u comma v is given. Find whether u is an ancestor of v or not. So any solution? So you can, this is basically like you must first pre-process the tree and then answer each query. So one main way will be, for each query you do you can traverse all the parents of v in the tree and find u, but this takes order n time per query and order 1 tree processing, but we can do better.
Discovery and finish times for v. The discovery and finish times of v, that segment, the time interval should lie completely within the time interval for the discovery and finish times.
Exactly. So what he says is, initially you have the tree, so perform the DFS and find the discovery and finish times for, that is start time and end time for each node, and then given a query of the form u comma v, u will be ancestor of v only if the discovery and finish time of v, say discovery time of v is some 5 and finish time of v is 8. So the discovery and finish time of v is completely within the discovery and finish time of u, say 3 and 10. So you can see that only if this 5 comma 8, the discovery and finish time lies within 3 comma 10, this v is in the subtree of u. So this is one of the uses of discovery and finish time. Are everyone clear with this? I mean, did everyone get it? This is one of the properties of DFS. So next is DFS trees. So once you do a DFS, the DFS will not have any cross edges, like it will not have any cycles, the DFS, the order in which you visited the DFS. So what you basically get is something called as a DFS tree. So in that example also we got a linear chain. A linear chain is also a tree, but even in a general graph, a DFS from any node will give a tree or a forest. I mean, basically the basic idea is you won't get cycles. Okay, what is a forest? It's a collection of trees. So but we call it as a DFS tree and not a DFS forest. Anyway, so the main point to note is, once you do a DFS, you won't have any edges, any cross edges between them. It will be a tree. Yeah. So yeah, I'll go to the next problem. It's called as nesting cuboids. So you are given n cuboids, each having dimensions, say ai comma bi comma ci. So you can basically, one cuboid will go into another cuboid if there is some rotation of the two cuboids in which all the 3 dimensions of the first cuboid will be less than all the 3 dimensions of the second cuboid. Find the longest sequence of cuboids you can enclose within one another. So say a cuboid of dimensions say 6, 3, 4 can enclose a cuboid of dimensions 2, 5, 2. That is because you can rotate this cuboid 2, 5, 2 so that the 5 matches with the 6, the 2 matches with the 4, and this 2 matches with the 3. So all three dimensions of this is less than all 3 dimensions of that. So these 2 cuboids can be enclosed.
You sort the initial coordinates of each. First you sort the lengths of each cuboid.
What do you mean? You mean the 3 dimensions, correct?
Then after that you sort it as per the, using the C++ or sort function.
How will you sort it?
Based on the first coordinate. The first coordinates are equal, then sort it as per the second coordinate.
Okay. Hey.
Therefore, each I think we have to calculate the longest subsequence such that the second coordinate will be less than the longest degree subsequence coordinate.
Okay.
So you have to apply that thing on the 2 coordinates of the second 2 coordinates of all the.
Okay. Yeah, he got the idea. So the main observation is you can enclose a cuboid of dimensions a1, b1, c1 into another cuboid of dimensions a2, b2, c2 only if sort a1, b1, c1. Sort so that basically sort these 3 numbers and sort a2, b2, c2 also. Only if the first number of this is less than the first number of that, and the second of this is less than second of that, and the third of this is less than the third of that, only then you can enclose the 2 cuboids. So instead of checking for all permutations of the first cuboid with all permutations of the second cuboid and checking whether they can be merged, you can just sort these 3 coordinates. So basically this will be 2, 2, 5, and that will be 3, 4, 6. So if this is less than this, and this is less than this, and this is less than this, only if all these 3 conditions hold, you can enclose one cuboid inside the another. Everyone got this observation? Are everyone convinced with it? So if 2 cuboids can be rotated and fitted inside each other, then the sorted version of the 2 cuboids must be enclosable. So now what we have is, so initially on getting the input, sort the dimensions of each cuboid. So we basically have n nodes, each for 1 cuboid. There's an edge from cuboid, there's an edge from cuboid I to cuboid j if I can enclose j. Note that if there's an edge between I and j, there cannot be an edge between j and I. Are everyone convinced with this? We can prove this because you are comparing only the sorted version, and each number of this is less than each number of this. So obviously each number of this cannot be less than each number of this, which is the condition for I to j and j to I. But if you didn't make this observation that the 2 dimensions will be sorted, you will not be able to prove that if cuboid A is enclosed inside cuboid B in some rotation, cuboid B cannot be enclosed inside cuboid A. That cannot be proved very easily if you do not have this observation. So the main observation is the sorted version, and then so if you have an edge between I and j, you won't have an edge between j and I. So basically what you have is a DAG, right? So what you need is to get the topological sorted version of this DAG. You cannot use the inbuilt sort, you have to apply topological sort.
Yes, case.
Okay. Yeah. So we'll see what topological sort is. Okay, so a topological sort of a DAG is a directed acyclic graph. So a topological sort of a DAG G equal to V comma E is a linear ordering of all its vertices such that if G contains an edge U comma V, then U appears before V in the ordering. Okay? Correct? So what we need is to get a topological sorted ordering of the graph, of this graph. So can anyone tell me how, assume you have done the topological sorted order, assume you got the topological sorted order. So basically for any two nodes U and V, you will have an edge only to going to the right in this final array. The longest path in the topological sorted sequence is going to be the answer. How will you find the longest path? Can you explain it?
So final vertex put a DP on.
Okay, so assume you have got the topological sorted order. So from 1 to n doesn't have any edge to the right of it, because according to our observation, an edge can go only like this, from left to right. So n cannot have any, it cannot have anything to the right of it. It doesn't have any outgoing edge, so you can surely not enclose it with anything. So you can only this cuboid. It cannot enclose anything. So answer for n is 1. When you go to n minus 1, take all the edges which it has to the right. So in the case of n minus 1, it can have an edge only to n if possible. So if it has an edge to n, then you can enclose n within n minus 1. So the answer will be 2 if there is an edge n minus 1 to n. The answer will be 1 if there is no edge between n minus 1 to n. Everyone agree with this? It's okay? Yeah, so basically for a general node I, take all the outgoing edges from I. So it will be equal to 1 plus max of ans of j such that there exists an edge for all I to j. So if there is an edge between I to j, take the maximum of all the answers of j for which I has an edge to, and that will be 1 plus, because you will enclose this also within them, and 1 plus max of ans of j, and the final answer will be the maximum element in this array. Correct? Given the topological sorted order, you know how to solve the problem. So how do we do the topological sort? So first, there is actually a order M algorithm for doing topological sort called DFS of G to compute the finish times f of v for each vertex v. So basically run DFS in this graph and compute the finish time for each vertex. As each vertex is finished, insert it into the front of a linked list and then return the linked list of vertices. This is just a modification of DFS, and this will return the topological sorted order. Is it okay? So since we are only making a call to DFS, this will run in order M time. The next problem is, given a directed graph, find the minimum number of vertices you must select such that every other node can be reached directly or indirectly from one of the selected vertices. So I'll explain the problem. So suppose the graph is, say this. What is the minimum number of vertices you must select so that you can reach every other node either directly or indirectly? So say you select this vertex, that means you can reach this node and this node directly, but you cannot reach all these nodes directly. Correct? If you had selected this vertex, you can reach this vertex, and this vertex directly or indirectly, but you cannot visit this vertex directly or indirectly. So the solution for this graph is picking this vertex and this vertex. Correct? So what is the solution?
Number of nodes with n degree 0.
Okay, he is telling number of nodes with n degree 0. He changed his statement